Welcome everybody to the session 21, part 1 of our course on mathematical methods of signal processing. I have prepared again a number of new pages which will be available from the corresponding web page after this session. And I will try to do it with the more abstract part at the beginning. I will see how long it takes. And then hopefully some MATLAB demonstrations, but I'm not sure if I can do this in public or if I can publish them. So one of the ideas that should be discussed at some point is the idea of invertibility. So if we are in the domain of complex numbers or real numbers, we all know that you can invert almost everything except 0. On the other hand, if you look into matrices, we all know that there are many non-trivial, non-zero matrices which are not invertible. Just take a projection operator or so on. So it's in a Banach algebra in general, so we have multiplication, in our case, convolution or pointwise multiplication. It's always an interesting question if a given element can be inverted. So for example, if you think of a moving average, normally you think that, well, it seems that I have lost some information, so how can I recover it? But you may look at the convolution operator, not on the time side, but on the Fourier transform side. So especially if you have a discrete convolution, so your measure is concentrated on a lattice, and for illustration, just take a measure consisting of Dirac measures sitting on the integer lattice on the real line. Then the Fourier transform is a periodic function, or as we say, it's a function on the torus. And it's quite plausible that it could be invertible because it's non-zero. So a function Fourier transform is constant and is continuous, and if it's periodic, if it's non-zero, it's invertible. It is one of the deep theorems of harmonic analysis. It's the Wiener inversion theorem saying if you have an absolutely convergent Fourier series and if the resulting function is free of zeros, then the inverse is also in the Fourier algebra of absolutely convergent Fourier series. So I will give a very much easier example of a sufficient criterion. So when can we be sure that the measure, the discrete measure, or any measure is invertible? So as it appears in nature, we often have some closeness to the Dirac delta. So of course, the Dirac delta is the unit element for convolution. So if you have some positive constant and you find out that your measure is not too far measured in the norm of the bounded measures from the identity, then you can expect that it's invertible. And in fact, we have an estimate for the norm. That's the statement of lemma 24. Actually, it seems that I was writing it twice. So it's the same as lemma 25, which has now a number rho here. And the estimate here is some involved number, which I will explain during the course, during the proof. It's a very short proof, actually. And it's the question of how can you invert a number which is smaller, which is close enough to 1? And then the answer is, well, write it as 1 minus x. And you all know that the inverse of 1 minus x is just a geometric series. So it's the formula of the geometric series which is coming into play. So the first step is, if we have our assumption satisfied, so the scalar in both formulations, the scalar in front of the delta is the same that you have in the estimate, and you have a strict inequality. So what we are simply doing, we're rescaling it. We say, well, we would like to take the inverse of this factor. So we take rho to the minus 1, multiplying everything with rho to the minus 1. The rho, which is with the delta, disappears. And what we get is a number which is gamma, which I call gamma, and that's the gamma of the above, which is less than 1. And so what we will do is we will just talk about this renormalized measure mu, which is now really close to the identity. So we have mu1 is not far from the identity. And of course, it's interesting to observe the norm of the Dirac delta is 1, and therefore this number 1 is essentially the norm of the element that we have. Now, because we have an element, this difference, which is having a norm less than 1, we call this element kappa. So this is the difference between our measure more or less and delta 0. And then what we are doing is we look at this measure and its convolution powers. We know that the convolution product of two convolution corresponds to the operator norm of a product of two operators, and that's clearly submultiplicative. So if you go by induction for every n or r in my formulation, you can say, well, convolve k 20 times by itself, then the norm that you get is at most, and of course many times better, but in the extreme case it's most, the r's power of this bounded measure, and that is decreasing because gamma is less than 1. So these estimates form a geometric series on decaying numbers. Maybe just as a remark, if k would be a probability measure, all the powers would be probability measures and all of them would have the same norm, and that would be exactly 1. I mean, you would have 1 to the power r, but that's just a side remark. So we have this kappa and we can form a absolutely convergent series because these powers are convergent because the sum over gamma to the power r from 1 to infinity or from 0 to infinity is finite. And we're in the Banach space, so if something is absolutely convergent, it will be convergent. So we call the sum of this sum of these convolution powers, I call it mu1. It will be our candidate for inverse of the mu1. What we can estimate is the norm of mu1 just by summing up, and that's the geometric series. And here you see why it's important that gamma is less than 1. And we claim that this is the left and also the right inverse. Okay, I was copying in a bad way, so you have to change the order here. And because left and right are equal in our commutative algebra of measures, we just do it for one case. So what is mu convolved with nu1? Well, you write the nu1 as a series. So the first term multiplying or convolving with kappa raises the power. So instead of summing up from 0, 1 to 3, we are summing up from 1 to 3, again up to infinity. Whereas delta 0 is the unit, so you get just nu1. But if you have a difference between a geometric series starting at 1 and another starting at 0, you have almost all the terms equal except the original one, which is kappa to the power 0. And there also in the geometrics formula, the standard rule comes in. If you don't do anything, you call it identity operator. So by definition, this is delta 0. Or yeah, maybe you should also use this convention already in this summation. So when you write nu1 is the sum of kappa to the power k, you should add that whenever you write k equals 0, that this is the delta. But this is like x to the power 0 is just 1, the identity in our group. So this is just one of the things that we have. And if we want to come back to the inverse, remember our mu was normalized, then we have to just take the rho times the inverse of the normalized vector. And that means whereas the norm of nu was controlled here by 1 over 1 minus gamma, we have to do it multiplied by rho. So this is just if an element in a Banach algebra with unit is close enough to the unit element, then it will have an inverse, and this inverse can be controlled by geometric series of the term which appears in the difference. That's more or less the moral that you should take home and to use. Now, very often, and especially when you have only discrete measures, then you would take delta 0 directly and some other terms, which may be even sitting anywhere. It doesn't have to be on a lattice or so. If the total sum of the coefficients is less than 1, then we know that if you take the difference of the norm, which means you throw away this term, this is remaining, and that means that you will have the condition satisfied. So any kind of perturbation of a discrete convolution operator by something which is not too big will give you an invertible operator. And that's quite nice, because in the Wiener inversion theorem, you do not have any control on the size of the norm. Whereas you see here above in this formula, we have a control. So roughly speaking, assume the difference is only 1/2. Let's say the measure minus the delta is only at most 1/2. Then our gamma will be 1/2. 1/1 minus gamma will be just 1 divided by 1/2 is at most 2. So the rho was not necessary in this consideration. So if your function or your measure is at a distance of less than 1/2, it's to the delta 0, it will be invertible, and the inverse will not be a nasty guy. The norm of the inverse will be, well, it's a geometric series, but will be just an element in the discrete bounded measures of norm at most 2. Also, if you remember, we had a comment and the connection between multiplication of polynomials and discrete convolution. So we were observing that multiplying two polynomials corresponds to convolution of polynomials. But we all know if you start with a polynomial and you try to invert it, even if the coefficients are very small, you never reach constant 1. Because the leading term is never cancelled out by the remaining terms. So this is a big difference between ordinary polynomials or finite discrete sums. What I'm saying more or less is the story that you cannot have a finite discrete measure sitting on finitely many points, which is inverse to a given other finite discrete measure, except you start with the delta 0, of course. So if you have delta 0 plus some serious contribution, as small as it may be, you need these infinite sums, but the good part of this story is you can do the inversion. Now, the invertibility, of course, tells us also, or can be transferred into a condition on the Fourier transform side. So the division of mu hat, as it is in our lemma, from constant 1 must also be must be gamma, and it means the difference from constant 1 must be less than gamma, which means the Fourier transform has to be free of zeros. So that's quite plausible, because if I give you a measure, which is maybe a discrete measure sitting on the integers, you're computing the periodic periodic Fourier transform, and you also have the inverse element. Together they have to multiply to constant 1, and you cannot multiply anything which has a 0 by some bounded function back to constant 1. So it's clear that this is a necessary condition, but it was Wiener's inversion theorem that in this very specific situation of absolutely convergent Fourier series, you can do this inversion directly. Okay, so this was just because I wanted to use and show you a few more things later on. Now, let me see what, maybe I have prepared some material for the proof that a mild distribution sitting on, supported on a single point has to be a Dirac. This was part of the discussion. But first I would like to show some other things to you. We have many different things, of course, to discuss now. One is how to use this pair of S0 and S0 prime, maybe combined with L2 to what I call the Banach-Gelfand triple, so how to make use of the Banach-Gelfand triple. But also we should demonstrate how to make use of the freedom that we gain by using this big space, which is Fourier invariant and so on. But first I thought I would like to tell you a little bit more about the usefulness of the space S0. I could give a long list, and within the time that I had today, I was trying to explicitly write down a few facts aside from those that have been already used in the discussion so far. So the first thing is, and the chapters will be relabeled also, but the first thing is that the zero space, so this amalgam space consisting locally of the Fourier algebra, globally in an L1, or the space that can be built within the Fourier algebra by this atomic representation. It has the good property that it has many invariance properties, most of them in the best way verified by the atomic characterization. So you reduce all your proofs to atoms, so elements in the Fourier algebra, which are living somewhere, but which have a compact support and with a uniform control on the size of the support. Or, which was the second most useful characterization, it's just the set of all the reasonable things. And in mathematical descriptions, you start with L2. In the more recent papers, I define the space even as saying, well, you take the bounded continuous functions or the C0 functions, which have an integrable short-time Fourier transform with respect to a Gaussian window. That would be one possible characterization. And if you start with this, you only need Riemann integrals, and you also get the Fourier inversion. You get the Fourier invariance of the space. So I would like to come back to the Fourier inversion theorem and reconsider it in the general case. So assume somebody has given you two L1 functions, two integrable functions. Then you can write down the fundamental formula for a Fourier transform. I just took a copy of the earlier version, but changing left and right hand side. So I'm going to start back from this. So what we can do is try to go once more over the proof and verify that you don't need any extension to the Lebesgue space, but whenever both your F and G are in S0, then all the involved elements are in S0, especially because it's Fourier invariance. And this in turn is important because we can use or prove Poisson's formula, or we have derived Poisson's formula in this setting. So we don't need a theory of temper distributions in order to deal with Dirac measures or Dirac combs. So what was the argument for the proof of the Poisson formula? Essentially, we were saying, well, the sum of, if you take the classical case with the lattice lambda to be the integer lattice on the real line. The statement was the sum over the point values of the function at the integer lattice is the same as the sum of the Fourier values at the integer lattice. Now, how did we arrive at this point? We were creating the periodic function, which means we are periodizing the function f. Now, S is nice, and it's in the Wiener algebra, and therefore periodization is perfectly meaningful. This is a sum, an absolutely convergent sum of continuous bounded functions. So it's a continuous function, and of course bounded, and everything is fine. So this sum is absolutely convergent. Now, then we were going to the Fourier transform side. We were doing, and this was the key step of the proof, we're doing the Fourier coefficients of this new periodic function. And we have been verifying using the periodicity of the pure frequencies with integer frequencies that these are exactly the Fourier coefficients of these periodic functions taken in the classical setting. But we are not in the dangerous world of Lebesgue integration, but we just have an absolutely convergent Fourier series because the restriction of the Fourier transform of our f is in little L1, so it's absolutely summable. So the last step is that the pointwise representation of this new periodic function at the value 0, which is the left-hand side of Poisson's formula, is the same as the sum, as this Fourier expansion on the Fourier transform side, which is f hat of n multiplied with e to the 2 pi I at 0, but e to the power 0 is always 1. So the right-hand side is the Fourier expansion of this periodic function at the value t equals 0. The left-hand side is the definition of the periodic function, and in between we were using all these other facts. So there is a well-known fact that it is not enough for a function in L1 to have both sides of the Poisson formula being convergent, and all the counterexamples are of course outside of S0, and actually also the sufficient condition, the convenient sufficient conditions that we are aware of and that you find in the literature can be seen as sufficient conditions for a function to be in S0. So one of the examples that one finds in the literature would be assume that the function f together on the real line, the function f together with its first and second derivatives are integrable. While this implies that the Fourier coefficients of this sequence are decaying like 1 over k squared. And that of course means that they're absolutely summable, but at the end this condition is just one of the many sufficient conditions for S0. So maybe at some point I will give you a list of more things. Now, Ferencz in one of his papers, joint papers, has discussed a long list of classical so-called summability kernels, which are used in order to come back from the Fourier coefficients to the original function. So in the classical situation, the situation is the following. You start with a periodic function. Well, when does it have Fourier coefficients? And for all the last century, it was clear. You have to assume L1, that's good enough. Now, with L1, you can write the Fourier coefficients. You get the Fourier transform if you have a continuous function. But it doesn't have to be good enough to recover. So what does it mean to recover? In the case of periodic function, you would write the Fourier series, and you would say, well, it's a series, so what is the problem? Take the partial sums. Now we have Fourier coefficients in the elegant writing of complex exponentials, so avoiding cosine and I sine terms, so that's just a replacement of through Euler's formula. So we take summation from minus n to plus n of what you expect to be the Fourier series expansion, which works for absolutely convergent Fourier series. So you say take the Fourier coefficients, use them as amplitudes for the pure frequencies, and choose more and more frequencies. And there are all kinds of problems with this. For example, it's fine to have quadratic convergence, convergence in the quadratic mean. So if the original function is a little bit better than integrable, but if it's square integrable, so if the peaks are at least very narrow, then you have convergence, but not pointwise, but only in the sense of the quadratic mean. We will come back to Gibbs phenomenon in a moment. So people realize that, well, if they don't take the, let's say probably what I assume is they were looking at the, computing the partial sums, and they were finding out that they start to oscillate. They oscillate in one direction. If you have an n, you make the n bigger, oscillate in the opposite direction. So on average, that should be okay. So they were taking so-called Cesaro means. Cesaro means simply means that you take, once you have computed 20 partial sums, you take the average over those 20 sums. Then you take more and more. Once you have 100 Fourier coefficients, you take the partial sums up to order 100, but you take a mean value over them. That, of course, means that you're using more and more of the original one, because let's say the first 10 are appearing already 90 times in this mean value over 100 or so, but only the new ones are contributing, giving a very minor contribution. Now, for us, it's very easy to understand what this Cesaro procedure means. It means, well, the Fourier coefficients are not decaying well enough. They're not summable. So let's make them summable by multiplying them with some numbers which are going to 0, but at the same time, as you do more and more of them, you're respecting more and more of the Fourier coefficients more and more substantially. So as we have seen in our case, we were doing this Poisson proof, we were taking the Fourier coefficients as the samples of a function. So we consider now essentially the same problem at the level of Fourier transforms. So what if the f hat is not decaying very well? Okay, then multiply it with some function g, which has the property that on a large domain it should be better and better close to 1, and that would make the integral better and better. So what was the idea of the proof? That we were saying, well, if we write it in this way, we would like to choose the g to be something which is a function which is having the value 1, so that if you dilate it, so it's dilation for rho to 0, you stretch it, this guy is going to constant 1, but we wanted to, I mean, we have seen that the inversion formula means you would like to have at the end f hat times constant 1 times a pure frequency. That's what you expect from Fourier synthesis. But you're not allowed to do it, so you're trying to do it approximately. Well, and that's mean you're taking a function h. I was writing here, take it for simplicity symmetric, then we don't have to write the flip operator anymore. Stretch it so that it will be closer and closer to constant 1 on larger and larger domains, and multiply it with the pure frequencies. And why? Because we would like to have at the left-hand side, which is here, so we have to go back from our function g to the Fourier transform. Maybe I should put the forward Fourier transform here. I will have to check it. Probably yes, but I have a symmetric function, that's why it's not relevant. But the main point is that this function is going to a compressed version of h hat, and modulation is, at least here, if I take the inverse Fourier transform, it should be translation. So somehow you can also say, well, we were starting from saying, well, if I know these integrals f against g hat functions, I would like to choose the g hat such that it's a Dirac sequence picking out the value at a given position t. And that corresponds to have the corresponding stretched version of its Fourier transform modulated. And so probably the f to the minus 1 and the f and the t and the minus t have to be checked here in the writing that you see here. But what we have here is when we multiply with a stretched version of the dilated stretched version, and now I'm more or less fixing this function, I'm saying, well, we're having an f hat, we're multiplying it, so we can view this as a Fourier transform of some guy, maybe very concentrated in our case, and we are saying, well, we're taking, because now we have proved the inverse Fourier theorem, if this is integrable, we can say this is the Fourier transform of the convolution. So what can we say here? So f hat times h hat. What can we say about it? Well, I was saying we were all the time, or we should all the time, to choose this h in S0. That's what it was relevant. Well, I was writing here the two lines. We know that L1 convolved with S0 is in S0. We know even bounded measures convolved with S0 are in S0. But on the Fourier transform side, this means Fourier algebra elements multiplied with S0 and are in S0. So the guy h here is in S0. F is a Fourier transform of an L1 function, but the product is S0. So yes, this is a nice function which is in S0, and therefore we can easily say, well, it will be the Fourier transform of some other guy. So it, of course, of f convolved with h. Or if we really write it out with the d rho operator, it's some other h which is compressed. So the condition that h at 0 should be 1 means that you stretch the 1 until it's almost 1 on very big domains. And here we compress on the time side the function so that we get a Dirac sequence. So we can say that there's something missing. Yeah, that essentially, yeah, I would say the formula, I should give a formula of this here. So on the left-hand side, this procedure, this f hat with a dilated version of h, is f convolved with some kernel, and this is an approximate identity or so. So this is helping us to get good functions where Fourier inversion theorem can be applied. So this was actually the strategy of the proof. But now, with this new refreshed look at the fundamental formula, we can say that whenever you give me some function in S0 with integral 1, so maybe here, sorry, here I have it, integral 1, the same as the Fourier transform at 0 equal 1s. If I stretch that Fourier transform more and more, I will get the integral of the Fourier inversion formula. But we will also ensure that these guys are integrable. Therefore, also, if you take a discrete version, everything is an algebra of absolutely convergent Fourier sums. And we have now the ability to show that this is, or I've seen that this corresponds to smoothing. Now, in our proof, we have used the triangular function, which is the convolution product of the boxcar function. And because the Fourier transform of the boxcar function is the sinc function, it corresponds to the sinc square function, which, as we see here, is actually in the Fourier algebra, because this is clearly compactly supported, and its Fourier transform, the sinc function, is in FL1. L1 intersected Fourier algebra is Fourier invariant, so we are inside S0 because this guy has compact support. Now, I wanted to mention and indicate a little bit that for the case that you have positive functions, so if your kernel here, the S0 of h is positive, then you have the mean value property. So just to indicate the sinc function is not positive, so you cannot guarantee. What is the mean value property? Well, assume you have a function f which is integrable and which takes values between some constant a and b. So for example, it's a bounded function and the sup norm is at most 1. Then if it's a real valued function, you know it's just moving between -1 and +1. So you're doing a smoothing by this S0 operator, so you're convolving it. I mean, you would not expect that you get functions which are larger than the original function. You have a kind of moving averages which should smear out the information. But we'll see it's not true without assumptions, but with this assumption, it will be true. So we assume now that our kernel h that should be compressed, and I just write it for the h itself, should be non-negative. And of course, we assume it's normalized so that if you compress it, you get the Dirac and not a multiple of a Dirac. And that this this integral is, of course, the same as the Fourier transform at 0. So it's the integral against e to the power 0. But because it's non-negative, the integral is also the L1 norm, and that's 1. And the claim of the story is, if your convolution kernel that is approximating the delta is non-negative and of norm 1, then of any function, range of the function values will be preserved. So if f is having values between a and b, the same is true for the convolved one. Now, we have already seen that we have this equality or so. Clearly, okay, here is missing a head. We also have that not h, but h hat. The Fourier transform at every point is, of course, is dominated by the sup norm, which is h of 0, h the L1 norm. But if the L1 norm is h hat at 0, you should say that the biggest value of all these values for a non-negative function, I have to repeat, for a non-negative integrable function will, on the Fourier transform side, will be achieved for z equals 0. So the hat here should be corrected or so. Okay, now we look at the situation of the lemma. You're giving me an integrable function, but also some side information that's maybe a positive function with, well, let's say it's a negative function with a certain range or so. Now, I claim that you can reduce the proof to a non-negative function f. And it's very simple, because if you have f being pointwise larger than a, maybe some negative constant, then you just subtract this negative multiple of constant 1 from the function. That's not integrable anymore, but it's still reasonable to convolve it with h, and so there's no problem. And the new function is having values between 0 and, of course, b minus h, because we have subtracted h. In reality, you may have pushed it upwards. So what we can say is that the convolution product f convolved with this new h is a convolution product of two non-negative functions, and that's clearly non-negative. We don't have to discuss this. So how can we estimate the size of the convolution product? Well, we write the convolution, this is a decent convolution product of ordinary functions now, by writing the expression in the pointwise sense. But what we know is that this guy here, everything is non-negative. So this guy is at most the supernorm of this, which is of course our b minus a. If it's non-negative, it's at most b minus a. And then the rest is integral hy dy, which is 1. So it has the control of this size. So kind of, yes, it's plausible. For example, you're smoothing boxcar function with a Feier kernel, which means the sinc square function, and you're getting a smooth version. So instead of having sharp edges, you're getting some mild edges. We can do such a thing in the MATLAB experiment. But why is this so interesting? Well, if you just take the partial sums, then you would have a situation of overshoot and undershoot, which is the well-known Gibbs phenomenon. I think I had it already in some of the slides, but I better do it with some MATLAB experiment in the next part of the session or so. Now, the other thing that I wanted to explain to you now is the usefulness of Gabor atoms from the space S0. So essentially, I would say that the windows or Gabor atoms that one should use should definitely not be general L2 functions. Especially the rectangular filter is not a good way to compute the short-time Fourier transform. The short-time Fourier transform with the rectangular window is actually showing bad concentration in the frequency direction. So even if you have a very simple, nice signal, to do it with a rectangular function will fill the phase space or time frequency plane with a lot of coefficients which are not relevant or not useful. So please take time frequency concentrated Gabor atoms for the analysis, but also for the synthesis. So what I would like to indicate to you, and it's just a draft of an idea, which I will try to make more concrete with the MATLAB experiments. I'm saying we have the following result. You are giving me your favorite function. It shouldn't be nasty, so you have to give me some function from S0. Then I claim that I can tell you that every fine lattice, even every fine irregular subset, but that's too complicated for explanation. So I'm saying every sufficiently fine lattice in phase space can be used to generate Gabor expansions with L1 coefficients. So what is the game? I'm looking down to the footnote. A lattice is called delta dense if you're taking the union of all these balls and if they are covering the phase space. So it practically means that you could take, in the one-dimensional case, I mean, if your signals are one-dimensional, so we're talking about audio signal processing, and your lattice would be of the form A set cross B set. So you're jumping by multiples of A in the time direction, and you sample on the frequency side by multiples of B. Then A and B both have to be small enough. Then the lattice will have the property that all these circles of radius delta 0 put at the lattice point with AZ cross BZ will, of course, cover the full plane, which is then just the Gaussian, the complex plane, so to say. So this is the story that I would like to tell you. So again, our role game that I like to play all the time is you are allowed to choose the gamma. Then I'm doing some computation and say, okay, delta like, I don't know, 1 over 5 is okay. And then you're allowed to choose your favorite lattice. Maybe you want to have a hexagonal lattice or a separable lattice of AZ cross BZ or whatever. It has to satisfy this delta zero density. But then I'm telling you, I have a recipe now to compute the coefficients, or not the Gabor coefficients, but some Gabor coefficients, which allow to represent the function f in such a way that you need for every lattice point, and now we have to remember every lattice point in the time frequency plane is corresponding to a time frequency shift operator. So if lambda has the coordinates t and omega, you're applying to the g your time shift t first, then you multiply with the frequency omega, and then you're using as amplitude the coefficients belonging to this point. But it's much more convenient instead of writing multiple sums, especially in the non-separable case. So maybe you have a hexagonal lattice. I mean, how would you sample it? I mean, how would you describe the coordinates? You can choose coordinate systems, but then different people may choose different coordinate systems or so. In this way, you're just saying, well, no, I have certain coefficients and they belong to certain points, and these points belong to certain building blocks in our Gabor series. Now, what we also have to say is it's not an individual procedure. So I'm not saying, well, I can do it for any f. And then also this is important to explain. It's not that I'm saying for every f, I have a recipe and then you give me your f and I compute the coefficients. Then you give me another f, and then you compute it, and I get completely different method or so. No, I'm saying I'm able to describe a linear mapping that goes from the whole space as 0 into the coefficient space, which is the L1 space. And that has the property that whenever you give me the f, I apply this mapping and say, okay, very quickly I get the sampling values actually of a short-term Fourier transform with respect to some dual window. And if you use these coefficients and you synthesize it, you will get back your f. Now again, here a word about the summation. It's an unconditional convergence. So if it's a double sum over time axis, frequency axis, you can choose to sum up first in the time direction, then in the frequency direction, or in the other way, or you can say, well, I take the big coefficients first. Then you say, oh, it's not good enough as an approximation. I take better. I mean, I take some smaller also. Yes, the more you take, the better it will be. And if you at the end have used all the relevant coefficients, either the big ones or the ones that you found interesting, you will have a very good approximation. And not just in some vague sense, but it's pointwise. So you can say, if you want to write it, f of t equals the sum of these coefficients times these atoms at t. That's nice. If you say I want to be sure that I have uniform convergence, it's fine. Therefore, you have it for L1, L2, and so on. So S0 is really a nice space that allows you to do these things. Now, one more or two more statements is this mapping that is creating the coefficients, and this is also what we can do with MATLAB, is obtained by just taking some dual window, some other window, and it's really dual in the sense that if I would have started with G tilde, you would get back G as the complementary part. And this is another element which is also a decent element, and you just take as coefficients the samples of the short-time Fourier transform of the function f that has to be expanded with respect to the dual window. So the story here is I'm describing in the S0 setting the atomic characterization where your choice is that you're having the atom G. I'm saying if your lattice is too coarse, I cannot guarantee, I'm not sure, but if it's fine enough, you can get with a certain procedure the coefficients. You just have to compute the dual window and you take the samples of the short-term Fourier transform. Now, if you choose a lattice which is dense in some sense, I mean, it's far from critical, so not A times B close to 1, but much smaller. So you have a little bit of freedom, then there are many possible coefficients. So the null space of the synthesis mapping is quite big. So many different coefficients represent the same function f. And then the question is, which one is the best one? And then the idea of minimal norm least square solutions is the best. Assume you are in R5 and somebody is giving you 12 vectors. And how can you represent with these 12 vectors a given vector? And the answer is, okay, there are many, many possibilities, but the set of all coefficients which are in R12 that represent the given element is having some dimension. It's an affine subspace of R12. Now, is that affine subspace containing 0? No, because clearly, if you choose 0 coefficients, you will get 0. If your original vector is non-trivial, then you will not be able to represent it. So if somebody wants to represent a non-trivial vector, the possible set of coefficients will be an affine space, which is not going through 0. So now think of R3, think of a plane not going through 0. There is clearly one point which is such that it has the minimal distance from the origin. So you would say, I mean, I'm taking the plane, I'm forming a normal through the 0 point, and where this normal hits, I'm getting the point in the plane which is closest to your original, to the 0. So it's the element which has minimal norm. And that's also what you get here. You're not just getting any set of coefficients, but you're guaranteed to get those coefficients which minimize the L2 norm of the coefficients that you could possibly use. So among the many functions f, I'm not just delivering you some norm, as we did previously in our proof, where we're just playing around and I was finding some way to produce some coefficients, which were good, but not the minimal norm coefficients. Now I'm saying we have the minimal norm coefficients. I think I better go to the end of the argument and make a break this time a little bit later. Sorry for this. So the key point will be this relationship. We were discussing the inversion formula and we were deriving it from the fact that Vg is an isometric embedding of the Hilbert space of signals into the signal space of images. So whenever you have a signal with finite energy f, so people say a function in L2, we are producing this short time Fourier transform with a window G, which we assume to be normalized, because then the L2 norm of VGF is the same as the L2 norm of the original function f. I was telling you, take the L2 norm squared of the function f as the energy, then the L2 norm squared of this here is the energy distributed in the frequency domain. Some people also call this the spectrogram, not just the short-term Fourier transform. So it's a probability distribution you're distributing the energy in the time frequency plane, so that you not only know which frequencies are important by looking at the Fourier transform or which times are producing a lot of noise because it's a time representation, but you know exactly which concentration of energy you have in the time frequency domain. Okay, so this was the argument to say that in this case, the adjoint mapping for the analysis mapping is the inverse on the range. And the Vg star, instead of taking scalar products with this family P set G, so these time frequency shifted atoms, we were now taking a synthesis mapping and we were using VGF. So now in the moment I'm here, I'm writing capital F for this as the amplitude. So we get a very nice representation formula. And at the beginning, or for us, this was an abstract mapping. So VG star is a mapping. We were seeing already that this is weak star to weak star continuous somehow, but essentially you could say, take it as a procedure where you want to get the coordinates in the complete orthonormal basis for your Hilbert space. So if you would say, well, I have a coordinate system already, I have used Gram-Schmidt to produce an orthonormal basis, then what is f against, what is the fifth coordinate of f? So I would say f against h and h5. And then, of course, what you would do is to hope that the integral is justified. You would push it inside and you would say, okay, this VGF of z against p z g against h. But that would be another short-term Fourier transform. Both of these guys would be in L2 of the plane, which by Cauchy-Schwarz would give you that the integral is well-defined. So you would say coordinate-wise, this is well-defined, but I would like to tell you a different story based on the methods that we have in our course already. I would say, well, in our situation, I have assumed that both f and g are in S0. And we have already used the argument that then VGF is also in S0 now of 2 or 2D variables, which means it's integrable. And that means that the bounded measure, which has this f as a continuous integrable function, it's even Riemann integral if you want. So it's that could be viewed as a measure now of our 2D. Okay, fine. But how can we do it? Well, there's a typo. We start to, there are some typos. It was done too quickly. I will correct it. We discretize this measure. So we choose a regular BUPU now on the plane coming from a two-dimensional BUPU. So of course, a two-dimensional BUPU could be obtained by taking a tensor product, so a direction, each direction is a partition of unity, and then you get it in this way. And then I would get the deep psi mu of this particular measure, mu induced by f. So what is it? So I'm writing in the formal way. F, hopefully, or I expect that I have this, that the integral, and in the formal expression here with integrating against the measure, I'm integrating against, okay, I should write deep psi mu f. That's missing here, okay. But then I'm trying to write out, well, how did we discretize a measure? We're saying we have to integrate the measure against the localized test function. And then this is something localized near the point lambda in the time frequency plane. And then you do the synthesis operator for delta at lambda. And this is what we have already seen. This is just a time frequency shift applied to lambda. So what we can see here is we have to take this limit for each f. And there's a justification that this is convergent. That's the first thing. Now, I would like to take this expression as an approximation to the original operator. So we are saying f goes to the short-term Fourier transform, then to the sampled, then multiplied with these coefficients, will give you a set of coefficients. And the point is that we have to prove, and that's the hard part of this statement, that it's not only true that, now I'm writing hopefully a correct expression, this Gabor sum, so the building blocks are Gabor atoms with shift parameters coming from the lattice. The amplitudes which are to come are obtained by looking at how big this f is in the area of the point lattice point lambda. So if it's very smooth, you could also say, well, in the first approximation, I just take the size of this fundamental domain times the value of f at lambda. But then I would say that this is a good approximation, and the problem is, can I do this such that it's independent, I mean that the level of approximation, which is easy to prove for lambda goes to 0 for fixed f, but that you can choose it uniformly such that for all f, the same density is good enough. Okay, so I'm just indicating the argument that I'm saying, well, if we are able to do this, we come into this situation, but with this, we can do iterations then. Actually, we would do it now with the sampling operator. So instead of mu psi, we would do f of lambda pi lambda g. And then we would see that this operator, very much like our measure, which was invertible, is close enough to the identity, now the identity operator. So how do you invert it? Well, you're trying to iterate on the error. So if you know that this operator, so maybe I call this the operator A, is close enough to the identity, then I can apply this to the inverse operator A applied to F. Later on, we will call it the inverse frame operator. And we will see that, of course, A inverse times A is the identity. So we have a perfect summation, but the coefficients have to be taken from some other element. And that can be pushed over to the dual window. So that's kind of how we'll do it. I just want to mention that for a general L2 function, you get L2 summable short-term Fourier transform, you get a continuous short-term Fourier transform, but once you start to sample, everything might be lost. So you cannot be sure whether you can even control the L2 norm, you're getting bad operators or so. So there are a lot of problems that you get and that are difficult to overcome, if at all, if you're not starting with an S0. Now, just as an end of this remark is that this intuitive method is working fine, and it even allows you not only to do this for S0 elements, we're using L1 coefficients, but you're using it also for L2, so you extend the mapping for the slightly bigger space L2, and you get coefficients in L2. Again, the window is just in S0, but the signal which is analyzed is in L2. Finally, we mentioned that the synthesis mapping also has to be good enough so that in a S0 dual window will do synthesis from sequence space L2 in the back into the Hilbert space L2. And it's even possible to extend it to S0 prime. So even mild distributions have a Gabor expansions with coefficients which are in the big space, which are in L infinity, but then the convergence has to be taken in the weak star sense. Okay, I think this is more than enough of theory, and I would like to take a short break now. Maybe give me maybe 8 to 10 minutes. I will try to stop, and I will try to do some of the things that we have done so far now using MATLAB, but I have to start my MATLAB. Thank you for your attention.